Welcome. This talk is about the LoopForest abstraction provided by NOELLE that organizes loops in a forest according to their nesting relation. This talk is for my class Advanced Topics in Compilers that I teach at Northwestern University. I've decided to open these talks to everyone, even if they're not professionally made, with the hope that they will be useful for anyone interested in doing compiler research while taking advantage of the NOELLE framework. This talk is organized in 4 parts. First, we're going to look at the forest, the concept of a forest provided by NOELLE, then the concept of a tree within the forest provided by NOELLE, then what you can do to modify the forest and what are the consequences of it, and finally, what does it mean to have a forest of loops between functions. Let's start with the simple case where we want to get all the loops of a given function using NOELLE. First of all, you have to fetch the function that you care about. In our case here, we use a function manager of NOELLE to get the entry point of the program, so the main function in C and C++. And then we ask NOELLE to retrieve all the loops or all loop structure of the loops that are included in the main function or in any function. Now, each instance of this container returned by getLoopStructures is an instance of the class LoopStructure provided by NOELLE, which only describe properties of the structure of the loop. What's the header? What is the latch or latches, or etc. Okay. But this container return is a flat representation of all the loops. In other words, it's just a set of instances of loop structure. But we know that there is a nesting relation between some loops, and any compiler class would have taught you that. And if you don't know what nesting relation means between loops, please check out my material for the class 323 on my website. So for example, here, just to give you a very quick summary, if you have this function, here you have several loops, and they are organized hierarchically. There is the loop 1 that contain the loop 2, which also contain loop 1 also contain loop 3, and you can see that there is a nesting relation between 1 and 2 and between 1 and 3. And there is also another nesting relations between the loops 4, 5, and 6. Now, you can prove mathematically that this nesting relation always will generate a set of trees for every loops within a function. That's why it's called, I call forest. And here they have the concept of outermost loops and as well as innermost loops. And nesting level as well. The outermost loop has the nesting level equal to 1. And then in this case, 4 and 1 has nesting level 1. 2 and 3 and 5 have nesting level 2. And 6 has nesting level 3. So how can we, from a flat representation of the loops, how can we organize them in a forest? Following the nesting relation of these loops. In NOELLE, this is simple. You just invoke organized loops in their nesting forest, and you pass whatever set of loops you care about. It doesn't have to be all the loops of a function. It could be a subset, whatever that is. The NOELLE will return an instance of the class LoopForest, which organize them in a forest. And the API of this abstraction LoopForest is in the header NOELLE core loopforest.hpp. What can you do after you have the LoopForest? There are quite a bit of API, but like an example of it, of a use of the abstraction forest is you have an instruction and you want to get the loop, the innermost loop that contain that instruction. So in order to do that, using the LoopForest, you just invoke get innermost loop that contains, and then you pass the pointer of an instruction. Can even be a basic block, and you return the loop that contain it. And that is going to be a loop that is included in the forest that you are using. If instead that instruction does not belong to any loop within the forest you're using, then it returns null pointer. And if instead the instruction does belong to a loop, then the return object is an instance of the class LoopTree, which represent an entire tree of loops. Another example of a forest that, or use of a forest, is that you can ask the forest object, give me all the trees that compose the forest. So for example, in our previous example here, we have 6 loops, but they are organized in 2 different trees. So therefore, the API gets trees of the forest object will return a container of 2 objects. So 2 instances of the class LoopTree, one that represents the tree 1 to 3 and one that represents the tree 4, 5, 6. Now that we saw the forest and how to use it to check out the trees, then let's go back. Let's jump into how to use a given tree of loops. 2 slides ago, we look at the tree visually. We look at the tree in this way. You have the loop 1, loop 2, loop 3, loop 4 organized in a tree. You following their nesting relation, and we call this, the overall thing is a tree. The LoopTree abstraction provided by NOELLE organizes loops as a tree of trees. In other words, we organize them as every loop create a tree, and a tree can be a subtree of another tree following the nesting relation. So in our case here, we have 4 loops, so we're going to have 4 trees, and then these trees are organized following their nesting relation. So the tree 1 represent the loop 1, or the whole tree that starts from the root loop 1, and the tree 1 is composed by 2 subtrees, tree 2 and tree 3, and the tree 2 is composed by one subtree, tree 4. Every tree has the concept of children, which represents the immediate subtree that compose that tree. So in this case, the children of tree 2 is only tree 4, and the children of tree 1 is tree 2 and tree 3. Notice that tree 1 doesn't have tree 4 as a child, because tree 4 is a child of one of its children, tree 2 in particular. That's why in the LoopTree abstraction in NOELLE, we also have another concept called descendants. Descendants is the union of all the loops included in that tree. So in other words, the descendants of tree 1 is tree 2, tree 3, and tree 4. And the descendant of tree 2 is only tree 4. Tree 3 and tree 4 don't have any children or descendants, so they're empty. Also, there is the concept of a parent, which is it points to the tree that includes that tree. So in this case, the parent of tree 2 is tree 1, the parent of tree 4 is tree 2, etc. Finally, we have the concept of loop. That is the loop of the root of a tree. So the loop of tree 1 is the instance of loop structure that describe the loop that compose the root of tree 1, which is the loop 1. So when you have an instance of the abstraction LoopTree generated by NOELLE, this is what you have in memory. You have a tree of trees with all of these fields. What can you do with a tree? Well, you can take from a LoopTree, you can take the instance of the loop structure of the loop that composes the root of that tree by invoking the method getLoop. And also you have other methods like getDescendants, getChildren to fetch the subtrees or the subtree of the subtrees, etc., of that tree, following the concepts we saw in the previous slide. Now that we saw the concept of forest and the tree of loops provided by NOELLE, let's see what can we do to modify the forest and what are the consequences. Let's assume that we have a tree or a forest. Let's assume we have a tree. The forest that is composed by a single tree, like this one here. And let's assume that now we are writing an LLVM pass that relies on NOELLE. We have this tree, and for whatever reason, we want to filter out some of the loops because our optimizations don't care about them for whatever reason. Okay? Maybe they don't have enough iterations or whatever is the reason you want to remove it. So therefore, what we can do is we fetch we identify the specific tree that we want to get rid of. In particular, we want to get rid of a node of a given tree. So in this case, we want to remove, for example, tree 2 from the overall tree. Okay? By simply deleting the object tree 2, automatically the abstraction loop tree or NOELLE will patch the tree automatically. So it will get rid of the node you ask to remove. It will relink the parent and the descendants accordingly, and it will fix all the fields of the related trees to recreate a tree coherently after you remove the node you care about. So at the end, you're gonna obtain a tree without the node you removed, and everything is coherent. Now, the nesting level that is stored inside the abstraction loop structure, and there is a dedicated talk about it in this channel, the nesting level of these loops didn't change by removing a tree. So the abstraction tree and forest, they can be modified by removing trees, for example, and it will not impact any semantics stored inside the abstraction loop structure. Finally, we can talk about what does it mean to have a forest within functions. Before, we got all the loops included in a function, and then we play with it. But in NOELLE, you can also ask, give me all the loops of the entire program, by not specifying which function you want to focus on. And we can even organize them in a forest. But the concept of forest, or the abstraction forest provided by NOELLE, is built using the nesting relation between loops within the same function. So in other words, there is no nesting relation between loops across functions for the abstraction loop forest of NOELLE. If you care about creating or instantiating the nesting relation between loops across functions, there is a different abstraction that NOELLE provides called loop nesting graph, and there is a dedicated talk about it. Okay? But for the loop forest abstraction provided by NOELLE, the nesting relation does not cross function boundaries. So in other words, if we have here two functions, foo and bar, we have three loops. The first two, 1 and 2, are nested to each other inside foo, and the loop 3 is inside bar. You can see that in the innermost loop 2 of foo, we invoke bar, which has a loop. But if you ask NOELLE, give me the forest of the entire program, now it will return you a tree 1 and tree 2, and they are nested to each other to represent the loop 1 and loop 2 and their nesting relation, and a separate tree that includes that represents the loop 3. Okay? And so they're not merged together. With this, I hope this talk will help you, and good luck.